Good morning, everybody. Excited to be here. Thank you so much for AWS OpenSearch team for inviting us to speak today. Excited to be here at the first event in Europe for OpenSearch. So what we're going to talk in the next 40 minutes is about enhancing AI and LLM systems with hybrid search. A few words about myself. I'm Ohad Levi, co-founder and CEO of Hyperspace. My greatest passion is around AI and data and everything that comes in between. I'm a product person in my DNA. Love to build new things and new innovation. In the last 2.5 years, I've been innovating Hyperspace to build the world's fastest search engine. So a few words about Hyperspace, and then we will deep dive into the target of the presentation. So our mission at Hyperspace is to exceed the limitations that exist today around real-time search, in specific when search is becoming more popular in AI, Gen AI, and LLM systems. We are based in Tel Aviv, in New York. We are around 20 employees. And our main objectives from a product perspective is to build a real-time search database or hybrid search database that combines both keywords and vector search in a single solution. This is pretty relevant to the session that we're going to have right now and how the combination of the two can really enhance LLM performance. The second distinction is from a technology perspective. We are a deep tech startup. And as such, we are designing a virtual chip for search that is able to deliver a significant step function in performance at scale and also cost effectiveness. So I think for everyone around, dealing with search in the last year was really exciting. On the left side, what we can see is classic search or keyword-based search that has been here for years. With high adoption, obviously being controlled by established solutions such as Elasticsearch, Solr, and OpenSearch, but having, I would say, minimal hype right now. On the right side, we see vector search that got significant momentum after the launch of OpenSearch and ChatGPT. And we see huge hype around it, lots of POCs, lots of excitement, but only a small adoption rate. Now, the question that arises from that is what's the future holds? Is vector search here to replace classic search, or is it actually here to complement it? So I believe that, I hope that this session can help figure this out. So what I plan to present here today. So first, a quick intro about vector search, why it's great, but it's not perfect, and what are the disadvantages that it has today. Then a quick recap about keyword-based search, known as classic search or traditional search, and then how we can combine them both to enjoy the best of both worlds. And throughout this session, we will also tackle the scalability challenge on how to deal with the billion scale and provide some tips and tricks on how to deal with that as well. So let's start with a quick and intuitive example. I have 3 daughters ranging in ages 6 till 12. And they really like Kung Fu Panda. And so I decided to start this presentation with a quick example of a movie recommendation system. Let's assume that they really like this movie, and they watched it 3 times already, and now we are looking for some similar movies that they most likely going to have as well. Okay? So we can take the description of the movie, and we can use vector search to find similar movies based on the description. So if we do so, what we can do, we can take that free text, we can use a language model and create the embedding, run a vector search, that's going to find the top K movies having similar description. And if we do so, this is just an example on how we can get, let's say, top 8 most similar movies. And if you're looking closely, after I got Kung Fu Panda at the first option, I also get in on the third and fifth, even 4 movies which are not kid movies. Okay? Enter the Dragon. And this might happen because of the Dragon Warrior words shown in the description. Okay? So how can we tackle that? How can we improve the relevancy, making sure that we don't get movies that are semantically similar, but are not related to what we were searching for? So again, a quick example of how hybrid search can help in that. So this is a very simple example. We just included some metadata filtering. We filter by genre and created some enforcement, some rule-based enforcement on the search. We also say that we don't want the title to match because we don't want to recommend on the same movie. And after this hybrid search approach, we get results which are much more relevant. Okay, so basically, search is everywhere. Search is the fundamental of many different applications, ranging from e-commerce, recommendation systems, even in fraud prevention is pretty common. And the key of search is similarity and relevancy. Okay? And that's the objective of every search architect, to provide the top possible relevancy for the search. So a quick recap about vector search. Let's do a quick survey. If you can raise your hand if you are familiar and know about vector search. Okay, 80%. Who is actually using vector search right now, today? Okay, around 40%. In production? Oh my God, only 3 or 4 or 5 people. Okay. So let's spend some time introducing vector search and what it is. So basically, vector search is here to deal with unstructured data. Unstructured data means videos, images, and obviously free text. We started by taking the object. It may be an image of shoes in this case, or just a free text describing a product. And we use a text or image encoder to transform it into a vector representation. Okay? The vector is just a series of numbers that presenting the object in a multidimensional space. Obviously, we cannot imagine n dimensions, so we can look on that on a cube, on a 3-dimension cube, and the representation in a vector actually helps us understand the semantic meaning of that object. And we basically, the value of semantic understanding is that we can understand the context of that question being asked or the search being done. So in this example, we can see that apple is a part of a group of fruits and is semantically similar to a banana. But we can also see that an apple is semantically similar to Google, forming a group of companies. Okay? So using the context that Apple was searched for, we can actually understand whether the user was meant for fruits or companies. Now, the agenda of this session is talking about LLMs and talking about generative AI. And actually, search has become a critical piece in every Gen AI and LLM system. Almost every LLM system has to have a vector database or a search database inside. The flow consists of, I would say, with 2 main phases. At the beginning, we take the object. The object can be, again, video, image, video, or text. We use an AI model like LLM, like GPT, to convert the object into a vector or embeddings representation. And then we index those vectors in a vector database. And once indexed, we can apply vector search algorithms to find the most similar items. So k-nearest neighbors is the algorithm being used. It's basically measure the distance between those vectors in those n-dimension space, and it's effectively able to find the top k most relevant results. KNN, brute force, is actually comparing all the permutations in that space. So if I have million of vectors in my index, it will just check all the permutations. This is not so effective and therefore not so scalable. So there is another group of algorithms called ANN, approximate nearest neighbors, in which you are reducing the accuracy in favor for some performance improvements in latency. I think one of the main or known algorithms is also called HNSW. So the strengths of vector search, obviously I can talk an hour about vector search, but this is not the target of the session. But to sum up the strengths, vector search captures semantics. It's also highly versatile. So you can work with a variety of data, unstructured data. And it's also quite good for fuzzy searching. You don't have to have an exact match. And it's really good when you need to relax the search a little bit and apply some fuzziness to it. By the way, in this example, we can also see a multimodal kind of an example where I can search by text in order to find an image. So search is gaining huge momentum and is great. But obviously, it's not perfect, and it has some disadvantages. So what are the main challenges in vector search? First, explainability. You cannot really explain the user why you got this result. There is no way to explain it, and in some applications, it's really important. Some companies that we speak with are coming from content moderation, so they need to block some content, and they need to explain the users why the content has been blocked, and you cannot do it in vector search. Number two is applying business logic. In some cases, like the Kung Fu Panda example, we wanted to restrict the search in some way. So in vector search, you are not able to do so. You cannot put filters and some hard-coded logic into your search. And the third is hallucinations. Hallucinations is typically being used as a term for large language models, but I'm using it in this case as well because vector search always returns the top K results. Even if none of them is relevant, you will always get top K, okay? And if the top K are not relevant, so this can be quite embarrassing. Let's take an example of a vector search challenge. So let's assume I'm in the medical space and I'm searching for Pfizer drugs for depression. So on the right side, I get the right results, but again, Pfizer might be misleading. And on the left side, I'm getting Lipitor, which is anti-cholesterol treatment, nothing related to depression. It's semantically similar because of the brand name, but it's not what I'm looking for in drugs. It can be dangerous. So be careful using vector search when exact match is needed. Okay, so that was a quick intro about vector search. Now let's move forward a little bit and let's introduce some hybrid search examples that actually combines vectors with classic search and functions that exist for years in products like Elastic and OpenSearch. So starting with metadata filtering. Let's take a a reasonable flow where I'm looking for a text like Air Jordan shoes, okay? And I'm trying to find the most similar items out of billions. And this may be a challenging task from a computational perspective, but also from a relevancy perspective. So how can we combine vector search with business logic and filters? So at the first stage, what we can do is to generate a list of candidates. Okay? We have billions of options in our index. And what we do first is put in some hard-coded logic or hard-coded filtering. In other words, applying metadata filtering. I can filter the data by category, by size, by other parameters. And then I'm getting a subset of candidates that may be millions, maybe thousands, whatever. And this smaller space of results getting into a scoring phase, where I can score the objects by similarity using vectors. So what I'm gaining from that, I'm gaining for that the option to apply rule-based logic into my search. I can do space reduction and run the heavy lifting ranking stage on a smaller amount of data, which is going to improve my performance and cost effectiveness as well, because I'm doing the heavy lifting in a subset of the data. Here is a quick example of that. So again, let's assume that I'm building an app, an e-commerce app, that instead of searching for shoes, I'm searching, like in ChatGPT, in free text, okay? And I'm searching for Air Jordan men's size 46 with a color twist, or if it's in the US, size 11. So what I can do, taking that long sentence coming from the user, I can analyze the query, and I can break it down between very well-defined filters that is obvious that the category that the user is searching is shoes, and that the size is 11 or 46, and the gender is men. Okay, but then I can run the vector search, which captures the semantics and understand what Air Jordan means or color twist means on the remaining of the results. Okay, so we can see that in that very simple query. Now comes the question, when to apply the filters. Should I apply the filters before or after the vector search? So the answer is obviously depends between pre and post filtering. And in this slide, I'm trying to give you some options about how to do it from an architectural perspective. So first of all, if you pre-filter, what you can do is that, let's say if you start by billions, you can apply the filters like we've seen in the previous examples, and then maybe you filter by category and you get down to millions. If you have millions, few millions of items, you can effectively run KNN over that, KNN vector search over that, which is pretty much limited to this amount of data. If your filters bring you down to, let's say, hundreds of millions, this approach would not be viable any longer, because the KNN, the brute force KNN, would not finish on time, and it would take seconds or even more than that to run. So basically, post-filtering is a fallback. It's a fallback for performance and scalability issues if my filters cannot narrow down the search aggressively, okay? So what I can do in this case, I can run an approximation algorithm like HNSW, which is quite efficient. It can run on billions effectively. But I would ask the model to bring more K candidates. So I can run, I can instead maybe of bringing top K of 10 or 20, I will bring 100 or 1,000. And then I will apply the filters afterwards. Why bring in hundreds? Because I want to have results at the end. I want to to have some options after the filters being applied. Okay. Time check. Okay. So after we spoke about combining vector search with metadata filtering, now let's talk a little bit about rarity-based scoring and applying some scoring techniques available today for many years in classic search. So for those of you that might not be familiar with TF-IDF, it's been here for many years now. It's been evolved for decades, and it's highly been used in search-based applications everywhere. The essence of the algorithm is to apply more weight for rarity of the object in the corpus, right? And we can see it on the right side. Rare words gets higher score. So for instance, if I'm looking on an email extension, gmail.com is quite common. So if you have a match on gmail.com, you will get a very small score for that. But if you get a rare email extension that is not highly being used, you will get higher score. And if you get repetitions, which is right there in the middle, you will get higher score. So that's basically the essence of TF-IDF, and BM25 is the way to aggregate multiple TF-IDF scores. So again, it's here for many years now. We can take a look here about intuitive example that really focuses on TF-IDF. So let's assume I put the score as 0. I set the boost as 1. I apply, similar filters like I did before, filtering for genres, kids, and animation. For the Kung Fu Panda example, what I can do here, I can do score equals rarity sum of genres. So in this way, maybe animation may be more rare than kids, and then I get higher score for that. But in this case, I decided to pick rarity sum. I can also do rarity max for languages. So if I'm searching for English and Spanish, obviously I might get different scores and use just the max in between them. And then there are lots of capabilities in OpenSearch and other tools today to do arithmetic operations, to do boosting on that score, and creating some very versatile, let's call it classic score functions, okay? So this is just an example for a TF-IDF-based ranking function. Okay, so what are the strengths for that? It's fast, it's accurate, it's highly explainable. You can explain versus vector search that you are unable to explain it. This is highly explainable. You can really explain the users why you have a match on that. And it doesn't require training like in vector search. You don't need to pass it through an AI model. What are the disadvantages or the challenges with classic scoring ranking? That it actually requires exact match. It doesn't capture semantics. So if you're searching for tiger and you don't have tiger, you have Panthera tigris, you won't get it, okay? And obviously vector search will understand the semantic similarity and bring it. Another example, going back into the Apple example, it's missing context. Okay, so if you're searching for Apple stock and run it on a TF-IDF, it might get confused between Apple the fruit and Apple the company. And vector search will understand the semantic and understand the context of that, and might find the right solution, the right thing to do. So what can we do to resolve those challenges of classic and hybrid search and vector search? We can do hybrid scoring, okay? What hybrid scoring means? It means that we get the score of vector search coming from the KNN algorithm, okay? We get the score from the lexical search that we just seen from TF-IDF, and we merge them together. This is not trivial as well. How do you merge scores that can come from two different scale? Okay, so there are two approaches. I'm going to touch them briefly today. One is score-based and one is rank-based. Let's start with the score-based. A score-based approach for unifying the two scores is to do a weighted average between them. Okay, I got a score from vector search, I got a score from TF-IDF, and I'm just putting some weights into that. In this case, 0.6 for KNN, 0.5 for TF-IDF. Obviously, after I normalize them, how do I decide 0.6 and 0.4? This is a good question, okay? It's not trivial. One, it can be rule-based, hard-coded from my experience, for my trial and error kind of interactions. And the second, I can use an AI model for that. I can use an AI model that can actually learn the conversion rates that I'm getting, the relevancy. There are some libraries or like learn to rank that can do that, but basically using a model to define those weights that deliver the highest relevancy. So taking the same example of Air Jordan men's size shoes, on the left side, using just vector search, it will only capture the semantics. Therefore, I'm getting lots of different items coming from different categories, but all of them are kind of Air Jordan oriented. On the right side, I have a hybrid search option with filters, with a hybrid scoring that combines also the category, and then I'm getting much more relevant results. And the other approach is RRF. RRF is taking, it's a rank-based approach, and it basically combines just the rank. So if I get top 10 here and top 10 here, I can just use the rank of that. And in this case, this is more effective when the scores are not normalized. They are not on the same scale, they are not normalized. It's too complicated to normalize them, and this is how I can do it in this approach as well. Okay. Now, we spoke about relevancy up until now, but let's talk a little bit about latency, performance, and scalability challenges, and how search can be scaled to a billion scale. This is a very interesting illustration showing what's happening right now in data and in the market. And we saw that data is actually growing exponentially. Okay, if it's structured data in blue, structured data means keywords, mean data organized in tables. And unstructured data is images, videos, and free text that, as we can see, even growing in a larger rate. So we see explosion of data, and we see the fact that billions of documents becoming a standard. So how do we tackle that? How do we manage to run effectively in real time when we need to run similarity search on billions of items? So there are a couple of tips or things we can do. First of all, we spoke about space reduction, using filters to narrow down the search only to the relevant subset of data. Second is moving to approximation, vector search. I mentioned HNSW as a very common approximation algorithm for vector search, but you can take a look on NN benchmarks if you're suffering from that. You can see here a comparison of different algorithms and their effectiveness running vector search at billion scale. In this case, the comparison is between recall and QPS, queries per second. And the third approach is domain-specific computing, is just making the hardware stronger and making a compute architecture which is purpose-built for search and is highly efficient in running that. And this is what we do in hyperspace. What we do is to tackle this triangle of search compromises that we frequently hear about and see with our customers, the need to balance between performance and accuracy, like we just seen in the previous slide. And also cost is becoming a very important consideration in the space of AI and LLMs. So what do we do to provide a significant step function and significant improvement? We basically program in a virtual chip for search, and in this way, able to provide a much superior performance at scale. So a quick recap about the session. We spoke about vector search, advantage, disadvantages, quick recap about classic search, and we spoke about hybrid search, that here to enjoy the best of both worlds, and also some tips about running at scale in production, which, as we see here, it's not so common yet. So many of you that are experimenting that right now are going to suffer from those challenges while trying to move into production at large scale. So thank you very much for listening, and we are here to help in any way or connect. Thank you so much.
At this time, we'll be taking questions from the audience. So if anyone has any questions, raise your hand, and I'll come to you.
Yeah, thank you for the excellent talk. So I had a question about, you said something about a virtual chip that this is related to. I didn't hear too much about that. Can you elaborate on that?
Yes, of course. So as you probably know, data and AI is exploding right now. We see what's happening with NVIDIA and how critical it's become to run on LLMs. There are other workloads that also need some custom compute power to be much more efficient. So this is what we're trying to do in hyperspace. We are designing a domain-specific compute architecture for search. What we are doing, we are implementing search functions on the hardware level, but we do it virtually. We do it virtually. We are leveraging the fact that there are cloud-based instances that we can program, and program in a way that they are highly optimized to run search at extreme scales, and also at very low kind of latency. So I will be happy to elaborate about that after the session.
Excellent. Thank you very much. Next question.
You have one here.
Do you see people starting to experiment with lots of different types of embeddings and sort of picking, choosing between them? Or
what do you mean by different type?
Like different ways of making embeddings or using different models to create the embeddings. Like, are vectors sort of like the new field type, and you're going to have a couple of different ones that you're playing with to see what gives the best results?
Well, I think obviously vector search is not such an used thing like everybody thinks it is. It's been around for years as well. People have been practicing vector search, I remember, like 3, 4, 5 years ago as well. But I think the biggest change was when large language models been introduced, and OpenAI and GPT, which made the embeddings be much more accurate and much more robust. And this is the hype that we're currently facing. Now, in one hand, you got large language models that are highly accurate. In the other hand, they are very cost demanding and also challenging from a latency perspective. So people are trying to balance between large models and medium models, and so it's a real science, and it's a big topic by its own. which goes, I think, beyond of the purpose of this session, but I think it's a big problem to pick the right embedding model.
I mean, I think as a quick follow-up, I'm excited to never have to do phrase search again, because I can just use my vectors for phrases and keep keyword matching as traditional text analytics. So.
Yeah. And I think as of now, none of the vector databases actually pick this up until now. Everybody just say, you bring your own vectors, embed them the way you see fit. But I think this is a great opportunity for search databases to be responsible on that part as well, and make it more intuitive and easy for people to use, having an end-to-end solution.
Thank you for a wonderful talk. Question to follow up the metadata-based search. Do you see examples of companies actually using more than metadata, like knowledge graph-based, to filter down to more contextual relevancy?
Okay, I think this is a great question, and I think I'm reading a lot about it. There are lots of discussions about knowledge graphs and use the fact that graph model pretty well relationship between objects. So I think definitely have a lot of potential. But for me, from my own experience, I'm mostly reading about it. I didn't have a chance to actually meet with people that are doing it.
So no production yet.
Not production, but not even POCing on that. I see lots of. It's cool. I'm reading about it, but I haven't met even a single one actually POCing on that effectively right now. But maybe it's there in the future to happen. Just feel free to approach. And thank you so much for the opportunity to come and present here.